So let's go ahead and get started on this. We left off yesterday here in 3.3, talking about global extrema. So if you remember we started off talking about local extrema, and we used things like the first derivative test. Then we discussed the Hessian matrix and the second derivative test. And then we got here to global extrema. And we just kind of gave some definitions, but we haven't done any examples yet. So global extrema, basically we're going to have some domain for the function, and we're going to be able to find the maximum value and the minimum value along that domain. Okay, so let's look at an example here. So we have that this theorem here tells us that if we have a closed and bounded domain, then we're going to have a minimum, an absolute minimum and an absolute maximum. So let's find all of the global extrema for this function here within the triangular region with these vertices. So basically what this is saying is it's saying, hey, limit yourself to just this specific region, but across this whole region, find the biggest and smallest value that this function takes. So I'm going to draw the region first. So, right, so in the domain of this function that we're going to restrict to is, so we're going to have a coordinate plane, right? So something like this, XY plane. Okay. And then we have this first point, -1, 0. Okay. 0, -4. Okay. And then we have 4, 0. So we have this point here. So the triangle here is going to be something like something like this triangle here. Doing my best to draw it. So we're saying just restricted to this triangle. Let's find the extrema here. So remember, the first derivative test tells us where local extrema can be, and that's like these kind of peaks and valleys here. But once we include these extra conditions of like restricting the domain to some closed and bounded set. So like, for example, this triangle here is just is bounded, right? So it, you can fit it on some finite sheet of paper, and it's closed because it includes the boundary here. Okay, and so because of that, we say this is a closed and bounded set. So we're gonna find some extrema, even if whether it's one of these kind of peaks that we have from the local extrema, peaks or valleys, or this along the edge of this, and we'll see more of this, better examples of this in the next section. We'll see that, what exactly I mean by like along the border, you can achieve a maximum here, right? That's the interesting thing that happens, is basically because we have a border, along that border, you can achieve another maximum, even if the derivative of the function is not 0, even if you're not at a critical point. Okay. So the way we do this is, first of all, we do the first derivative test. We find some candidates, and I'm going to outline these steps a little more explicitly on the next slide, but we'll start by just finding some candidates. And to do that, we're going to start with the first derivative test. So if we take the total derivative of this guy, then we get y plus 1, and then x minus 2. So there's a critical point. So a critical point at 2, -1. And the thing with these sorts of problems is that you want to check that this critical point is actually inside of this domain, inside of your domain D here, or whatever it's called. So in this case, 1, 2, 1, yeah, sure enough, that there's your critical point. So that's one of our candidates right now. So I'm going to keep a running list of candidates for extrema. So the candidates can come from critical points. But where else can they come from? What else can we do? So the interesting part here is that what we're going to do is we're going to take the boundary of this region and we're going to check along this boundary to see what happens. In order to do that, we need to write these boundaries as equations that represent these boundaries. So for example, this boundary right here, you can write as y equals, this boundary part here is just the line. The y-intercept is -4, the slope is 1, so we get x minus 4. Okay, this top line is pretty easy. This is y equals 0, right? It's a horizontal line through through y equals 0. This one here has a negative slope of 4 and y-intercept at -4 as well. So y equals -4x minus 4. Okay. So yeah, make that a little more clear, -4x minus 4. Okay. So these are the three parts of this line. And what we can do is in this equation up here is make these substitutions. So on y equals 0, then we're going to see that f of x is equal to, so we just plug in 0 here, we just get an x. Okay. So now that we have it this way, we just treat it like a single variable problem. We take its derivative, f prime at x is equal to 1. So there are no critical points here. No crit points, right? And then on y equals x minus 4, things get a little more interesting. We get f of x is equal to, again, we're just, this f of x equals x came from plugging in y equals 0 up here. Now we're going to plug in x minus 4 up here. So we get x times x minus 4 plus x minus 2 times x minus 4. We're going to simplify all this. We get x squared minus 4x plus x minus 2x plus 8. Simplify this a little bit more. X squared minus, looks like minus 5x plus 8. Let's see. So now we're going to take this derivative, f prime of x, set this equal to, and set this equals to 0 once we take the derivative, 2x minus 5. So basically what we've done is we've found equations for these parts, plugged them into this original function, and now we're treating that as a single variable problem, and then finding the critical points here. So then there's a critical point at x equals 5 over 2, right? And then to find exactly where it is on this line, right, we plug in x equals 5 over 2 to this line here. So we get, that must mean that y is equal to 5 over 2 minus 4, which is -3 over 2. Okay, so then this here gets added as a candidate on our list. So we get 5 over 2 comma -3 over 2. So I'll try my best to draw that here. It's about here. This point here is a candidate. Okay. Okay. Now, lastly, we need to check on y equals negative 4x minus 4. Okay. So now we check this substitution. We put it in here. So let me go ahead and do that. So we get f of x is equal to x times negative 4x minus 4 plus x minus 2 times negative 4x minus 4. Let's go ahead and simplify this. So we get negative 4x squared minus 4x plus x minus, or plus 8x plus 8. Simplify all of this. We get negative 4x squared. Combine all of these terms. We get plus 3x plus 8. Again, we take this derivative and we get negative 8x plus 3. And when we set this equal to 0, we get a critical point at x equals negative 3/8. Okay, so then y, the corresponding y value is going to be negative 4 times negative 3/8 minus 4, which simplifies to 3 halves minus 4, which is negative 5/2, I believe. Let me double check that. It's 3/2 minus 4, which is 8/2. Yeah, that's minus 5/2. So we get a negative 3/8 comma negative 5/2. Okay. If we look over here, we actually see it's going to be somewhere like right here. And the better my drawing would be, the more accurate the original drawing was, the more accurate these points would be. These should have, oh no, they don't have the same y value. This should be lower. So yeah, that makes sense. Okay. Cool. Okay, and that there should be our, those should be the points that we now we're going to check these points, right? Because so far we've just said, okay, we've done things and we found this list of candidates. Okay, and the question is, what do we do with this list of candidates? Okay, so what we're going to do here, is we're now going to test these points, and I'm running out of space here, so I'm just going to scroll down a little bit, and we are going to test these points in the function. So we're going to test these points. So we're going to say, what is f of 2 comma negative 1? Right, and so we're using this formula here, xy plus x minus 2y. So we get 2 negative 1. I'm already forgetting. Plus 2 minus 2 times negative 1. Yeah. Okay. We simplify this. This gives us negative 2 plus 2 plus 2. So that's a positive 2. Okay. And then we're just going to plug in all of these into this function and see which one's the biggest and which one's the smallest. And that's going to basically, what we've done so far is we've said, okay, if there's going to be a maximum or a minimum, and in other words, if there's going to be an extremum, it's either going to be at a critical point of this original function, or it's going to be somewhere along the boundary. Those are the only two options. That's what our, that's basically what all of this was saying. Okay. If you actually, actually for this, you'd actually have to read the proof to actually see all that. But that's basically what all that says. If you have some kind of closed bounded domain, then the extrema are gonna happen, and they're gonna happen either at a critical point of this function inside of the interior, or along the boundary somewhere. And to find the ones along the boundary, you have to kind of do this. Someone's asking a question about a little typo I may have made. Okay. So this is minus 4x. Yeah, so there's a little mistake here that's going to change some stuff. It's good that I find it now rather than later. So let's use red to clean this up. So I did some arithmetic wrong here. Minus 4x plus 8x should simplify to 5x. Okay, so this should be plus 5. This should be a 5/8. And that means that this should be a 5/8. And so when this simplifies, it's actually negative 3/2. And so this should be this 5 and this 3 should be switched. So then over here in my drawing, oops, let me bring back that line. So over here in my drawing, that dot, they actually should be at the same height here. You get something like this. There. Okay. Good catch. I'm glad we cut it now rather than later. Okay. Cool. Okay. Yeah. So like I was saying, these are going to be the candidates, right? So this, if there's going to be an extremum, it's going to be somewhere here. Okay. And so we're going to say, we're just going to, we've done all the calculus to find these, but now it's just like, okay, which of these is the minimum? Which of these is the maximum? Okay. And so we just plug in these 3 points. So we say 5/2 comma negative 3/2. This is going to equal 5/2 times negative 3/2 plus 5/2 minus 2 times negative 3/2. So this simplifies to negative 15/4 plus 5/2 plus 6. So this simplifies, this takes a few more steps, but this is 10/4, so it's negative 5/4 plus 6. And then 6 is 24/4, so this is 19/4, which is equal to, you can write it as basically 4 3/4. Okay. Okay. I wouldn't normally write it. I'd normally be totally cool leaving it as 19/4. I just want to make sure that I can compare it and I can tell which number is the biggest, right? So 19/4, maybe you can see that off the top of your head. Oh, that's just 4 3/4. But I'd like to have it written down so that we can compare them more easily. Okay. And last but not least, we plug in negative 5/8, comma, negative 3/2. And so we get negative 5/8 times negative 3/2 plus or minus 5/8 minus 2 times negative 3/2. Okay. And then we just do this arithmetic game. So we get positive 15/16 plus, or I guess minus 5/8 plus 6. So again, we get, now this simplifies to positive 6, positive 5/16 plus 6. And so it's 6 5/16. I could simplify this, but this is already kind of in this form. It's kind of a mixed number. Okay. So remember, this function on this restricted to this domain, the function has to have a global maximum and a global minimum. Okay, that's what this theorem up here says. There has to be one somewhere. These were the only 3 possible points it could happen. Okay. And because of that, Actually, should I have also been, I also need to, actually, I forgot some candidates here. The other candidates that you always have to check, so this list grows, are these points originally. I forgot, you have to check these points as well, these vertices. You don't always, the vertices aren't always there, but you have to check these vertices too. And so we add these to the list of candidates. They don't take work to find, but it's extra work that you have to plug in. So almost forgot about them. Glad we didn't. So then we can check these candidates here. And then so we have f of -1, 0 is -1 comma times 0 -1 -2 times 0. So we get a -1. Okay. Then we have f of, what is it, 0, -4. 0 times -4 plus 0 minus 2 times -4. So this is a +8. We have f of 4 comma 0. I'm glad we checked these. Plus 4 minus 2 times 0. So this is just 4. Okay, cool. Definitely glad we checked these. So yeah, so again, we're looking for where you could possibly have a minimum or maximum. Again, that could be a local min, that could be a local extrema in the interior. So just go ahead and find a critical point. And the funny thing about this is that you don't actually have to do the second derivative test, because you don't actually need to check whether it is or isn't a local extrema, because you're going to check that when you go to check your candidates. It ends up coming out for free once you check your candidates. And then you also want to check along the boundary, and the way you find it along the boundary is, well, on the straight, like on the straight paths, or if they're given by some function where you could write y in terms of x, you break it up into the points where you could write y in terms of x, and you check those as a single variable case, and then you also check the corners. You always check the corners because something could be happening there. Okay, so then you have this list of points, and you just plug them in manually, and you see, okay, where's the biggest point and where's the smallest point? And in this case, both of them happened down here. So in this case, they're all happening at the corners of the shape. So in this case, you get the -1 and the 1. So an important note is how we would write the answer to this. So I would say something like, there's a max value is 8 at 0, -4. And then there's the min value is -1 at -1, 0. Okay, so sometimes they're asking for the maximum, sometimes they're asking for the maximum value. So the maximum is where that actual point is, that actual point that you plug in. In this case, this one. The max value, so the subtlety, remember value is, whenever they say value, what they mean is like an output. So if they're saying where's the maximum, where does the maximum happen, they're looking for the input. If they're saying what is the maximum value, they're looking for the biggest output you can get. Okay, and that in this case is this. Okay, in this case the phrasing was kind of vague, but and in something that's written by hand, you can kind of I would just like formally write my answers like this. Something that's like on the online homework, they're usually more clear about what they're looking for. You can tell by the text box. Sometimes if it says find the maximum value or the extreme values or something like that, then it's asking specifically for these outputs here. So it's asking specifically for this 8 and this -1. Okay, and doesn't necessarily care about this part here, this point. Okay, and as far as the in this section, you get a lot of like they have like ordered pairs and like blanks separated by comma. And so that's clearly they're looking for this part here. Okay, cool. So we kind of, we made our way through this problem. It was pretty involved, but I mean, it took 2 pages. But I want to kind of formally just like summarize the steps for finding these global extrema. Okay, so we start by shouldn't we use x equals 5/8 when y equals 4x minus 4? I'm not. So here we got a negative 5/8 when we got 4x minus 4, and so that point got plugged in right here. Did I do that correctly? Yeah, right here. Should it have been positive? No, you get a negative sign. Yeah. Okay, cool. Okay, so in short, I mean, you can break it up into these 2 steps, but obviously I left a bunch of space here because I'm gonna fill in some of the blanks. But basically your 2 steps are find the candidates and plug in the candidates. The question is, how do you find the candidates? So that's kind of what I'm going to go through here. So like 1A, you're going to find critical points in the, or inside the domain. Okay, this is like setting df equal to 0, right? So that's find your critical points inside the domain. Remember, that's the first thing we did, setting this equal to 0. And then we got y equals -1 and x equals +2. And then the next thing is find so I guess I didn't think about how to write this, but on the lines here, so on the chunks, we can write y in terms of x or x in terms of y. So find candidates on the boundary. Okay. And then part C is just check the corners. So I guess maybe here I'll say like write for part B, write x in terms of y for those for those edge pieces. So it's basically you do the inside, then you do the edges, and then you do the corners. Okay. And then this is just going to give you this list of candidates. Okay. And then once you have that list of candidates, you plug in the biggest value, and then, the biggest value output is the maximum value. And of course, the smallest value, the smallest output is the minimum value. Okay. Cool. Let's breathe there for a second. Any questions? Okay. Cool. So this kind of summary here at the end ends up being a nice segue to the next section, because this section basically we found local extrema, then we found global extrema. But for this section, whenever we find this little region, it's always going to be these kind of polygons. It's going to be triangles. It's going to be squares. So you can kind of follow these steps where you check along the edges, and then you check, or you actually check you find the critical points, then you check along the edges, and then you check the end, the kind of corners there. Now the question becomes, what happens if we can't do this thing? What if if we have a more complicated boundary, like the boundary isn't just a bunch of lines that meet at these points? That's what we're going to learn about in the next section. So that uses something called Lagrange multipliers. Okay, so let's go ahead and we can go ahead and switch gears here, and for the rest of, well, I'm actually running a little bit early. I have one more example here I can do for this section. It just, I'm worried it might take a little longer, but I think I have the time for it. Yeah, I have one more section here, one more example I can do in this section. So we're finding the absolute extreme values. So notice this one explicitly says the values, so that when we're looking for the outputs, the biggest output, the smallest output for the function, for this function here on this rectangle here. So once you get some practice, you can kind of picture what the region is on your own and kind of fill it in. But when we're first starting, I'm probably gonna keep drawing it every time. So in this case, it's a rectangle. It tells you that it's a rectangle, but you can also figure that out by saying, okay, x goes from -2 to 2, and y goes from -1 to 1. So we get something like, it's wider than it is tall, so it's going to be something like, okay, this is kind of the region that we're looking at here. Now we're gonna, well, maybe when we get there, we're gonna want to label these points, and so we can figure out what these points are and what these lines are when we get there. Let's start, of course, by finding the critical points on the inside. So let's take df of this function, and we get 2x and we get -2y. So if we set this equal to 0, we get a critical point at 0, 0, right? And of course, from our picture, we can see that that is squarely inside of the rectangle there. So if we're keeping a list of candidates, so then the first one we're going to write is 0, 0. Okay, so this is like step 1A, right? Sometimes this step is going to be easier than others. This case was pretty easy. Sometimes this total derivative might be a little harder. But in any case, we have something nice here. We get, we want to now find some equations for these lines here. So in this case, we get along the line, this here we have y equals -2. That should be a negative. -2, y equals +2. Should be a 1, right? -1 and +1, and this is x equals +2 and x equals -2. Okay, so that's kind of what all of these, the edges are represented by, right? Again, we're just using these inequalities to figure that out. So then we just kind of go through systematically and do all of these. On x equals -2, I'll start there and kind of just go clockwise. Then we get f of x equals, I should switch color there. F of x equals 4 minus y squared. So then f prime, I should say f of y here, because we made a substitution in this case. We made it for x, so now we're going to do everything in terms of y. F of prime of y is -2y. So then you get, so then if you set this equal to 0, then you get y equals 0. So now you're getting some kind of critical point of, in the single variable case, at x equals -2, y equals 0. So we'll add that to our list here, -2, comma 0. So -2, 0. Okay. So on, now we do y equals 1. Then we get f of x is equal to x squared minus 1. So then f prime of x is 2x. So again, we get x equals 0. Okay. So now we have x equals 0, y equals 1. So over here we add 0, comma 1 to our candidate list. So let's see these. I should be adding these to my picture over here. So -2, comma 0 is right here. 0, comma 1 is right here. And you can maybe see the pattern of the points we're going to get on for all of these. And so we get on x equals 2, we get f of y again equals 4 minus y squared. So the calculus all works out the same. And so we get x equals +2 and y is still equal to 0. So again, that's over here. I'll show the work just for the sake of having complete notes here, but you can imagine we're just going to get this point down here, right? So y equals -1 is what's missing. And we do the calculus, so we get f of x again equals x squared minus 1. F prime of x equals 2x, so then x equals 0. So we get 0, comma -1, and so of course that's this point here. Okay. Now we want to find the corner points here. So that's all that's missing, right? Because so that was 2b, or 1b, I should say. We found the candidates on the boundary, right? And now we're going to check the corner pieces here. Okay, now the corner points, I should say. Now the corner points we could label. So this is on x equals 2 and on y equals 1. So we get 2, comma 1. This here is 2, comma -1. This is -2, -1. And this is -2, +1. And so we get, we'll just write all those here. 2, 1, -2, 1, -2, -1, and 2, -1. Okay. So we have this nice long list of candidates. And so we can just check all of those. I was going to try to fit it in here, but I think it's best if I just do this on a new page. So I'm just going to take all of these and plug them into and just test them here. So we start with f of 0, 0. Maybe I can scroll up here so we can still see. And the function was x squared minus y squared. So we do 0 squared minus 0 squared, and we get 0. Okay. Then we do f of -2, comma 0, and we get -2 squared minus 0 squared. So we just get a +4. And we do f of 0, comma 1. So then we do 0 squared minus 1 squared. So we get -1. Okay. F of +2, comma 0. So we get 2 squared minus 0. So we get a 4. +4. And then missing one here, 0, -1. A lot of these are going to be repeats, right? Because there's some symmetry to, there's a lot of nice symmetries to this function, which is why you're seeing a lot of the same arithmetic come up multiple times. So we again get 0 squared minus -1 squared, which is again -1. Okay. So that's up to here. Now we just check the corner points. So we have f of 2, 1, which is going to be 2 squared minus 1 squared, which is 3. Then we have f of, so what are we noticing about all the corner pieces here? We can work smarter, not harder. See that, right? What's going to happen to x and y? We're just going to square them. So none of these negative signs actually do anything, because once you square them, you get the same thing. So you can see that all of these are actually going to equal the same thing. These are all the same, right? Because since you square x and y, negative signs don't matter. Minus signs don't matter. Again, that's geometrically, that's there, if you were to graph this, there's like this rotational symmetry. Okay. So if we were looking for the extreme values, that means we're looking for the biggest input and the biggest output. So the max value was 4. And in this case, it shows up twice, but that doesn't change the fact that it's the max value. And then the min value is -1. Okay. Cool. Any questions on that? This one went a little quicker. I think the arithmetic just was a little more repetitive, so we ended up just kind of breezing through it, but the principles are all the same. It's this kind of outline here. And the outline, this outline here is going to be helpful in the next section, except that this step of checking the candidates on the boundary is going to be a little more involved in the next section. We're going to go ahead and switch gears to the next section here. So we're going to switch to 3.4. I've already changed the, changed that. Okay, so here I have a cool little picture, and I want to actually take some time to talk about this picture a little bit. So this picture here is going to kind of exemplify kind of what I'm talking about. Why when we restrict to a certain domain, we're always going to have some kind of maximum. So you see here, there was a local max here. There's a local max at this point here. Okay. And if we didn't have this restriction, it looks like this function would probably just keep going forever and just keep, it looks like, oops. If we went this way, this function's kind of starting to slope upward. And if you just kept letting it go, it would just keep going forever and ever and ever. But as soon as you cut it off and you restrict to this little region down here, okay, then you can see that over here, we actually get a point that's taller than the little hill here, okay? And that's the maximum value that's achieved if we just restrict to this little, it looks like a little circle down at the bottom, okay? And so that's kind of what we have. That's kind of the principle at play here. If we restrict to just like a finite, the technical terms are closed and bounded region, then somewhere on that region, either somewhere inside or somewhere on that boundary, we're going to see a minimum value achieved, okay? You can notice even more so here that there's no local minimum here, but there has to be a global minimum here, somewhere like over here, right? Because, at the boundary, it's just going to go get as small as possible somewhere, okay? And so our goal now is to figure out how to use calculus to find these 2 points here, because in the last section, all of our regions were these nice polygons. So we could just say, okay, well, now you can write this side as x is a function of y, and so, or y is a function of x, either way, and make some substitution in the original equation. Now just treat this as a single variable problem and find some nice points, and then check corners as well. Okay, but now if we have like a circle here, the question is like, oh, how do we actually use this circle to actually use to find where the critical points could be? And so I guess before I do that, I want to add a page here so I can, oh, come on, show you kind of, so if the region, so the region, oops. So it might look like, for example, a shape we all know and love, a circle, right? We know how to write the equation for a circle, right? Right. So this is just an example. The shape might be different. We have an equation for this, right? We have a nice equation for this. And so everything that we're going to, all of the regions we're going to have, even if you can't necessarily break it up into nice parts where x is a function of y, you can have some equation for the actual region. So in this case, you'd say something like x minus, whatever the center is here. So AB. So x minus a squared plus b, or y minus b squared, is equal to r squared, right? You may think, okay, I have this equation, but how can I use calculus on this? So the trick is that we can think of this, or so I guess this is the boundary. The whole region would you'd write less than or equal to, but and we'll see some examples of what I mean. So like the region itself is less than or equal to, but the boundary is just a straight up equal to, right? Because everything in here, the radius is smaller or whatever, however you want to think about it. But the point is that this here is what the boundary looks like. We could think of this boundary. This is the level set of this function I'm going to call g of xy, called x minus a squared plus y minus b squared at r at c equals r squared. So the boundaries of these regions, before we were doing this thing where we thought of it as a polygon and we broke up each line as some x is a function of y or y is a function of x, and we just said, okay, now just makes the substitution. Now we're going to say, well, we can't do that here, but we can say that this whole thing is a function of x and y, and what we're looking at is a level set, and we can do some calculus with level sets. For example, so some facts, right? Or maybe just one fact I think is that's going to be useful for us is that the gradient of this function that we just cooked up is normal to this boundary. Okay, right. So in my picture over here, that would be like, I can draw something like at this point here, the gradient point of this function, not the function we're trying to note. This is not the function we're necessarily trying to minimize. In fact, it's usually not going to be the function we're trying to minimize. Okay, this here is the gradient at this point here. Okay, and so the gradient is always kind of pointing outward away from this blob here. And now in this case, it looks like a circle, but what if it didn't look like a circle? So what if you had kind of more of a blob looking thing? It does have to be kind of smooth. Then the equation for this might not be super obvious, and then this is just an example. We're probably not going to get anything like this. But if you had some equation for it, that described what this shape looked like, then the gradient of that shape would be normal to this point, this boundary here. Okay, at every point. Okay, so that's just like a little geometric reminder of what we can do with level sets. So we're going to bring that together with some calculus, and we're going to get these things, this method called the method of Lagrange multipliers. So that's, I keep saying Lagrange. This is how you would spell that. So the name of some mathematician. So you may have noticed that since we started chapter 3 in earnest for 3.2, things have kind of picked up. I feel like we keep introducing these. You know, things are getting real when everything's named after some old mathematician whose name you can barely pronounce. So we had the Hessian. Now we have Lagrange multipliers. We also had Taylor's theorem, which I guess is easy to pronounce, but it's kind of when the stuff started getting heavier. So we have, like I said, we're going to say that S is going to be some level set of the constraining function. This constraining function is, or it's sometimes called a constraint. The equation itself is called a constraint. But basically, we're thinking of this as the boundary of some region. So S, we're going to think of the boundary for some region. Okay, so this first part, in its purest form, the method of Lagrange multipliers is just about the boundary of some region. But basically, we're going to combine this with what we know about critical points and finding stuff in the interior to be able to figure it out across a whole region. But the method of Lagrange multipliers is specifically for the boundary of some region. And then what we're looking for is, so we're trying to find the extrema, but as you may have noticed, a lot of times we're looking for candidates of extrema, so that the phrasing of these is a little weird. But if you already have an extrema, then it's going to satisfy the certain property as long as the gradient of the constraining function is not 0 at that point. So this is like a little technical thing, like just make sure this doesn't happen, and then this nice equation is going to work. And that equation is, let me write it here, the gradient of f at p is going to equal the gradient of g at p times lambda. It's a lambda thing where lambda, again, it's the Greek letter lambda, is some real number. Remember, these gradients are vectors, and so this is just a scalar multiple called the Lagrange multiplier. Lagrange multiplier. Okay. So this is, conceptually, this is actually pretty interesting, right? Because what you're saying is that the direction of growth for the function, so the way we should break this up, there's like two functions hanging around, and you're like, okay, what are the two functions doing? F is the function that you're trying to maximize or minimize. You're trying to find the extrema of, so right, P is an extremum of F. And G is the constraining function. G is the function saying, hey, restrict yourself to just numbers which are, or vectors which are x squared plus y squared equals 1, or something like that. It's going to be some kind of constraining function. Okay, and this is the function, and F is the function you're trying to maximize. And what this is telling us is that where the extrema are, the two vectors are lining up in the same direction, just maybe scaled a little bit. Maybe, maybe G is a little bit longer, or maybe they're pointing in technically exact opposite directions. But the point is that they're lining up. Sometimes sometimes we say that this means that the vectors are parallel because they're kind of pointing in the same direction, just different lengths. Okay. Okay. So I'm giving you a second to write this down, but I think the best way to learn this is to jump in and do some examples. Okay. So I have an example here. So we're trying to find the minima and maxima. I should say, I'm saying extremum. I should probably be saying global extremum. Usually if we drop the global or local, right? If we drop that, it usually means global. So if you don't have an adjective, we usually mean global, but I should probably be saying like, is a global extremum on S. So it's global with respect to S. So here we have this function here, f of x plus 2y with this extra constraint that x minus 2 squared plus y minus 2 squared equals 1. So I'm going to start by going through this problem. If you just see this problem, like, how do I do it? I don't want to understand conceptually what's going on. I just want to find the steps to do it. Okay. Well, according to our method of Lagrange multipliers, we're going to want to compute the gradients of both of these and then figure out where they are equal. So not equal up to this scalar multiple. So compute the, so this here, we're given f of x. We're going to use, since we have this constraint, this is the level set. This equation you can think of as the level set for this function g of x, y, right? So if we just let the left, basically you're going to move you're going to move any constants to one side, or I should use the way you should think of it is you're going to move all of your variables to the same side, and then if there's constants left over, it doesn't really matter. Technically, you could expand this out and move even more constants to the other side, but it doesn't really matter. The point is that you just let if you get all of the variables on one side, then you just let all that stuff equal the g of x, and that is your constraining function. And so we're going to first compute the gradient of f of x, or f, the gradient of f. In this case, that is 1 and 1, 2. Okay. This case, it doesn't depend on x and y, but we'll see some cases where it does. Okay. And then we're going to compute the gradient of g. This one's a little more involved. This is 2x minus 2, comma 2y minus 2. So there's a secret chain rule happening there, but the derivative of the inside is just 1, and so it doesn't actually show itself. Okay. So we get this, and we get this. Okay. And so we're trying to see where does this equal this times some lambda. So what we do is we want the gradient of f to equal lambda times gradient of g. Okay. And so we're going to set this up as first as vectors and then as a system of equations. And so lambda right now, as of this moment, is an unknown. There are various methods to solving problems of Lagrange multipliers. And so I'm going to kind of hopefully get to some more of those examples tomorrow, some deeper examples. But today I want to get through this one and kind of just kind of use this example, which is computationally simple, to kind of show off some stuff conceptually once I'm done. Okay, so let's compute the gradient of f. We already have the gradient of f, so we've computed, I should say, the gradient of f and the gradient of g. So we have lambda times 2 times x minus 2, comma 2 times y minus 2. Okay. Then this, right, so remember when we multiply by a scalar, that gets multiplied across. So we get 2 lambda x minus 2, 2 lambda y minus 2. This is equal to 1, comma 2. So I'm going to move this off to the side here. Oops. Okay. And we could turn this it's an equation of vectors, but we could just turn it into a system of equations. So we get 1 equals 2 lambda times x minus 2. And then 2 equals 2 lambda times y minus 2. Okay. And what we really care about is finding x and y that satisfy this equation. Okay. But this is two equations and there are three unknowns, right? There's lambda and then there's x and there's y. And so methods for actually solving this might not be that obvious right away. And so what we can do is we can basically solve for lambda and then set these. There's a couple of methods that we can use here. And so we can say, no, we have a third equation. That's right, I remember now. So there's a third equation here that we can throw into the mix because we have to remember that x and y need to satisfy these equations, but we're also have a constraint up here, right? So this constraint gets added into the mix. So we actually have a system of three equations and three unknowns. So there's some chance of solving it. Now, the third equation might not be linear, or actually none of these, they might not be linear, so you might have multiple solutions and stuff like that. So, but remember, this is just, this whole method of Lagrange multipliers, what it's doing is it's replacing our methods for finding candidates along the boundary. And so now we're going to solve this system of equations, which is actually a little easier because what we can do is we can say over here, this tells us that x minus 2 is equal to 1 over 2 lambda, and y minus 2 is equal to 1 over lambda. Okay. And we can make these substitutions over here. So we get 1 over 2 lambda squared plus 1 over lambda squared is equal to 1. So then we get 1 over 4 lambda squared plus 1 over lambda squared is equal to 1. So then we get, there's some arithmetic happening here. 5 over 4 lambda squared is equal to 1. Solve for lambda, we get lambda squared equals 5/4. Okay, multiply both sides by lambda squared. And then lambda equals plus or minus the square root of 5 over 4. Okay. So now this is going to come back over here and we get the system of two equations. We get two systems of equations. We get 1 equals 2 times 5/4 times x minus 2. And then 2 equals 2 times 5/4 times y minus 2. I guess you can also just plug in over here to these equations over here. You can also plug the lambda in over here. That might be easier to solve for x and y. I think I am going to do that. So take these. Sorry if you were already writing that down. So x minus 2 is equal to 1 over 2 times 5/4, which is 4/10. Cool. And then that means that x is equal to 2 plus 4/10, which is 24/10, which is 12/5. Okay. And y minus 2 is equal to just 1 over 5/4, which is 4/5. And so then y is equal to 2 plus 4/5, which is 14/5. Okay. And then we can do something similar. Remember that we got a plus or minus over here. So then the minus is just going to, so we get x minus 2 equals 2 over 2 times negative 5/4. And the arithmetic, well, I guess no, the arithmetic is not exactly the same. We get negative 4/10 here. Then we add that and we get x is equal to, so that's 2, that's 16/10 which is 8/5. And so then we get, do something similar for y. It's equal to 1 over -5/4, which is -4/5, which tells us that yet 6/5. Okay. And that, so then this tells us our candidates here in the middle. I'll put it right in the middle. So our candidates were this point 12/5, comma 14/5, and then 8/5, comma 6/5. Okay. So you don't always get the nicest numbers, but these are just some fractions, not too bad. So now, so let me pause for a second to explain what I've done. After this, it's the same as what we were doing at the beginning of class today, the examples we were doing earlier. But up to this point, it's been very different, right? We use this thing called the method of Lagrange multipliers, which involves you take the gradient of the function, take the gradient of this constraining function, whatever the constraint is, you move all the variables to one side, turn that into a function, take its gradient, set them equal to each other, but you multiply by this lambda thing. Okay, that gives you this system of equations along with the constraint itself. This gives you a system of 3 equations, or I guess, if this was in 3 variables, then it would give you 4 equations. It gives you n plus 1 equations and n plus 1 variables, where n is the number of variables of the original equation or function. The point is that you get these equations, usually 3 equations in 3 variables, and then you can solve. The solving part is going to involve some creativity. In this case, I just isolated x minus 2 and then moved it over and then plugged it into this other equation and solved for lambda, then plugged the lambda back in and solved for x and y. And then there was 2 values of lambda, so I get 2 different ordered pairs here. Those are my candidates. Now, since I'm restricted to this circle, or this here is a circle. Since I'm restricted to the circle, I know I'm going to have a minimum and a maximum. And so one of these is going to be a minimum, one of them is going to be a maximum. I'm going to go ahead and give myself some more room here and plug these these candidates in for and test them in my original function. So 12/5, 14/5, that's equal to x plus 2y. So that's 12/5 plus 2 times 14/5, which is 12/5 plus 28/5. So things are working out nicely. I don't have to say fifths as much anymore. So this is 40 over 5, which is 8. Whole number there, nice. And then now f of, what's the other one? 8/5 and 6/5 is 8/5 plus 2 times 6/5. So I get 8 over 5 plus 12 over 5, which is 20 over 5, which is 4. Cool. So that means that it wasn't asking for the values. It was just asking for the minima. So I'll just say we have a max value of 8 at 12,5, 14,5, or sorry, 12 over 5, 14 over 5. And then the min value at the other one at 8/5 over 6, 6/5. Cool. And that's how we find these extreme. This is how we found the difference between this and the last section was how we found the candidates, right? There are no corners to check. It's just and the other difference is that we're just checking along the boundary. We're not checking on the interior of some region. We'll get to some examples where we do that, where we check on the interior of some region. We'll do that tomorrow. We'll see some of those examples, but this is the example I wanted to go through. And I think tomorrow, the first thing I'm going to start with, because I'm running out of time here, is kind of Okay, so we saw computationally how to do a problem like this. There's a lot of, there's a lot of steps because there's a lot of finding, solving systems of equations, which vary in difficulty. But then you just kind of plug it in and you're done. But what I want to start with tomorrow is looking at this problem, drawing some pictures of what's going on in this problem so you can understand conceptually why this equation it works and why the Lagrange multipliers do what they do. Yes, so someone's asking, are these candidates just on the boundary? Because there's an equal sign here, right? The constraint is telling us we just want the actual circle itself, not the disk that fills the circle, just the circle itself. So we're just looking at the boundary of what would be this disk. In this case, it turns out that if I made it the whole disk, it would not change. But in general, it might change it. You might have some critical points on the inside. So the only difference, and I'm going to write it out as a list of steps. If you remember the list of steps I ended with last time in the last section, this just changes step 1 a little bit for the finding the boundary components part, but 1A is still the same, and I'll talk about that tomorrow.